open keel. Yeah, keel is opening. Now I copy the same program. I'll execute. Yeah, I'll just close this project and open new. Yeah. So project, new microvision project. So let me save it on the desktop. I'll create a new folder here. Yeah, I'll just name it as DCM, DC motor. I'll open here. I just want to save it with the name again, DCM. So this is the project extension, microvision PROJ, microvision project. I'm saving it. So this is what I did now. Now I want to choose the controller. You know this already because I've shown when explained you the part A programs. Our controller is LPC 2148. Because I'm writing the program for this controller, just select it, say OK. Now it says copy startup.s to project folder and add file to the project. You have to say yes, because when you're writing embedded C program, startup.s is required. When you're writing directly the ARM assembly program, startup.s is not required. Now since I'm writing an embedded C program, startup.s is required. Say yes. Yeah, now the target is created. Now and under that you can find the startup.s. Now I'll go for adding the new file. Now where I'll be writing my program. Now I'll just it will take me time to write this entire thing. I'll just copy and paste it because I've explained the program. Copy this, so paste, and my functions also. Yeah, these are my functions. One is clockwise and anti-clockwise. Copy. Yeah, paste it. So this is my program. Let me save it. Yeah, I'll save it as again DCM and the extension as C program dot embedded C program it is. Yeah, you can observe now. Yeah, let me make a few initial alignment for better clarity. Okay, and let me push all this comment section towards right. Yeah, I think it is fine. Okay. Now all comments are also there. You can go through. I've written the comments just to make you understand the program easily. It's okay. Now, so this is done. Let me save it because star, because just now I wrote it. So save it. Yeah, star gone. Okay, now the program is saved. Now this program I have to add here. Add to the source group 1. This is just a file which is written and saved, but this is not yet added to your project. How to add? So right click on this, add existing file to the source group 1. So this is DCM. You can observe it's a C file. So so it's directly went to the folder which is created on the desktop. Now add, close. Now you can see here DCM.c. So now you got to do a few things here. Yeah, sorry, the semicolon is missing here. Okay. Yeah, semicolon was missing. That's the reason it was showing error. Now I'll say, let me save it again. Now, observe. Now I have to do a few settings here. First, let me go to the startup.s. I'll open this. This you got to remember configuration wizard. So this PLL setup by default it will be checked. It is in checked state. You have to uncheck this. Why? Because we are using LPC 2148. So it operates with 12 megahertz frequency clock. If this is checked, so that 12 gets multiplied by 4. So but LPC 2148 can operate with only 12 megahertz clock frequency. Now you got to uncheck this. Uncheck it and save. See, startup.s, I made change, it is marked shown as star. That means I've done some changes, I have to save. Now if I close without saving, so it will be again checked. Now save it. Now star is when it is saved. Next go to dcm.c. Yeah, that and yeah, one more change is and I can close this startup.s now. Yeah, so this I made the change. I uncheck the PLL setup. Next you have to do few more changes. So right click here, options for target. This you have to do because I want to dump this program to my controller. Now without doing this you cannot. See here there are many tabs. You got to focus on only on target, output and linker. Now target, you can see here 12 megahertz. I told LPC 2148 operates with 12 megahertz. You got to make sure that whether it is 12 megahertz. Yes, it is 12 megahertz. I don't do anything. And then you have to check this. Use microlib. That is what you have to do in the target tab. Next, go to the output tab. Here you have to check create X file because X file is required. When I compile and build, so X file is required because I cannot write this direct C code into my microcontroller, burn into my microcontroller. Now what you can write or burn to the microcontroller is the X file, hexadecimal file after the machine code. Now I have to check this. If this is unchecked, again it will not create the X file. And one more thing what you have to do is in the linker, you have to check this. Use memory layout from target dialog. Now after doing this, just say OK. So now you can go for compiling. See, compiled, 0 errors and 0 warnings, observe here. And next build. Yeah. So here, since I have done that settings in the target 1 and checked create X file, creating X file, and X file is created. Where will be this X file? It will be in the same folder. Now from where I have stored my project, DCM. See here, dcm.x file. This is the file which will be burning into the microcontroller. Okay, we'll come back to this later. Let me go here. Yeah. Now before going to the Proteus simulator to show the output of this, let me simulate it here itself by going to the debug. So I have to say OK. Now first go to the debug mode. And since we are not going to see the output, here in the register, now this is the output you are seeing on the port. When you want to see it on the port, you go to the peripheral and then GPIO, general purpose input output slow interpret, and which port we are displaying. We are using the output port 0. Click here, you'll get this. Yeah. Now pin cell 0. The pin cell 0 is not here. What we are doing is all the port 0 pins, we are making them to operate in the general purpose input output mode. I'll proceed step by step execution. This statement is under execution. I'll press F11. Yeah, this statement is executed. This is the hexadecimal, this is the machine code. This is not required right now. Let me minimize. Yeah. Now, next what we are doing, IO0 DIR. So 9, this is the data we are assigning. Observe here, IO0 DIR. Now what it should do, the 8th bit, 9th bit, 10th bit, 11th bit. So this bit and this bit will go high. And when they go high, when this and 8, 9, 10, 11, when this bit and this bit goes high, the corresponding port pins will be acting as output pins. Observe now this P0.8 and this is P0.11, P0.8 and P0.11. Sorry, this is the 8th bit of this register and the 11th bit of this register. What it will do, it will make the corresponding port pins to access the output pins. Now we have made them to act as the output pins. What pins? These two pins, and to these pins you have the motor connected, DC motor connected. One terminal of the DC motor is connected here, another terminal of the DC motor is connected to this. Next, while one clockwise, I'm calling clockwise. Observe now, in clockwise I'm clearing IO0 CLR initially because I want to start with the stop state of the motor. Now to IO0 CLR again I'm assigning this data. Now this will become high here and this will become high. When when these two go high, the corresponding port pins will go low. P0.11 and P0.8 will go low, and the motor is in the off state. The motor is in the off state. Now, and I want to make the motor remain in the off state for this many iterations. If I press F11, say it stays there. Yeah, it came out. Okay. So because this loop, once it finishes, you need not keep pressing F11 for so many 4 lakhs times. You press it simultaneously back to back 3 to 5 times, it will come out. Now I want to make the motor run in the clockwise direction. To make the motor run in the clockwise direction, now I want to make this bit high, because I'm assuming this is this is P0.11. When I make this high, the motor runs in the clockwise direction. For the data is 800. This is 8, this is 10, and this is another 0, and to the left side here you have all zeros. Let us not worry about that. Now what will happen? IO0 set here. This particular bit will go high. Yeah. Now when that goes high, the corresponding, see here, this is still 0 and this is 1. 1, 0. P0.11 is 1 and P0.8 is 0. Now since it's connected, I'm saying to this pins, the motor is connected, the motor will start running in the clockwise direction. Now the control will return back where it goes to the for loop, and it stays 10 lakh, iterates here only for 10 lakh times. So 10 lakhs I've given a little big. Yeah, it came out. Now I'm calling anti-clockwise direction. So till this time, this is 1 and 0. The motor is still running in the clockwise direction. Now anti-clockwise. Click here. Anti-clockwise. Now how to make the motor go off? How to make it go off? How to make both of them what? 0 0 0 0. For that, IO0 CLR and this data. Observe here. Both are 0 0. The motor in the off state. I continue the motor to be in the off state for these many iterations. Yeah, and then it came already. It's finished. And then I make this bit as I. In IO set, this is I. So P0.8 is I and P0.11 is low. 0 1. This will make the motor start rotating in the anti-clockwise direction. And after this, where it will go to the for loop, and till the microcontroller finishes these many iterations, 10 lakh iterations, you have the DC motor running in the anti-clockwise direction. So this is what the execution which I showed you in the Keel simulation. So now we'll go for the real simulation of the DC motor using the Proteus simulator. Let me start the debugger here. Okay. Let me do it again. Compile, build. Okay, X file is created. So now I'll go to the Proteus simulator. Let me minimize all these things. Yeah, I've done the initial settings already here. DC motor. Let me open. This is the Proteus 8 version simulator, 8.6. Okay. Now this is the basic connection which I showed you in the previous class. This is the LPC 2138. It is not LPC 2148 because in the simulator there is no LPC 2148, but LPC 2138 is exactly same as LPC 2148. This is what you can use in the LED program which I showed. This is what we used. So this is the power supply, because low power controller, it operates with the voltage 3.3 volt, and this is the active low signal RST bar. Now it's going, the low signal, it is active, and this is the quartz crystal which supplies all the clocking requirement for the microcontroller, and you have all the port pins here, CP 0.0. Now we'll do the connection. Now if I ask you a question, how to make the connection? Now even for the DC motor there is a driver. Now if you want, you can connect directly the DC motor to the port pins, which are the two port pins which we are using here, P0.8 and P0.11, because I have written the program like that. See, P0.8 P0.8, this is what I have to use. I cannot use any other port pins because my program is written using P0.8 and P0.11. Now if you want, you can take a DC motor, connect it directly to P0.8 and 0.11, but it will not run that accurately and precisely. Now every external device will have its own controller, or sorry, instead of controller I have to say it as the drivers. Now I'll use the driver here, this one. Now L293D, okay, I'll use it. Now through this I'll connect it the DC motor. Now this is what I need, and yeah, let me calm this side little because you can have a clear view. Yeah, now this is what the L293D, it's the driver for the DC motor. Now it's not only the driver for the DC motor, the same driver can also be used for the stepper motors also. In the next experiment I'll show you, how to use the same thing for as the driver for the stepper motor also. Now you can observe here in this VSS is there. To this you have to apply plus 2 volt. To this you have to apply the plus 5 volt, and it has totally 4 inputs. So pin number 2 is one input, pin 7 is another input, pin 10 is one input, pin 15 is one more input, and 4 outputs as usual, and 2 grounds. Now let me do this connection first. Now what I have to do now as per as the program what I have written, P0.8, I'll connect it to one input. I have only 2 inputs. Now I'll not use this. I'll not use this, and even enable also I don't use. I use this in and this in. And P0.11 here, I'll connect it to this. Next, I told this 8 is connected to plus 2 volt. I'll use a shell. Yeah, I'll rotate it. You can rotate always by right clicking. Rotate clockwise. Okay, let me rotate it for one more time. Yeah, this is fine. I'll connect the positive of this to the positive terminal of the battery, and I need a ground also. Ground. Here, let me place, connect the other terminal to the ground. Now, and similarly for 16 you have to connect, and this is not 1.5 volt, I have to give 12 volt. So you double click there and change it to 12 volt. Okay. Now I need one more battery. Let me copy this segment, copy to clipboard, paste from clipboard. Yeah. If I copy paste, I can avoid all those yeah, let me put little this side. Yeah. Connect it to this, and this is not 12 volt. I have to make it as 5 volt, and from here again it's connected to the ground. This is what we did. Let me bring little this side. Yeah, this is the another battery. This is 5 volt battery, this is 12 volt battery connected here, and these two grounds must be connected again. Connected here, and this ground, let me connect it here itself, it goes there. Okay, so this is what the connection you have to do. Now the stepper motor, DC motor I have to connect. Where is the DC motor? I have the DC motor here. I have already placed it here, motor DC. I'll bring it here. It has only 2 terminals. Let me place here. Yeah, little up. Okay, here. Now I've connected P0.8 to 2 and P0.11 to 7. Now these are the, when you are using these two as input, these are the outputs which you have to use. 3, I'll connect to this, and 6, I'll connect to this. It's done now. The connections are done. Now I have to load my program, X file which is generated to this. Now how to load? I have to double click on this. I have double clicked on this. I get this. I have to look at choose my X file now. Browse. Now my X file was on the desktop. Now so DCM was the folder. DCM. Now this is DCM.x. Open. Okay. Now this is programmed now. I've written my X file to this microcontroller. Now what I need to do is say run the simulation. Now when I say run, you can observe the simulation is running. Initially it was in the stop state. Now it is running in the clockwise direction. So for some delay, it will run in the clockwise direction. Now stopped. Now runs in the anti-clockwise direction. So now again in the clockwise direction. Again in the anti-clockwise direction. Yeah, one thing, anti-clockwise direction, it is going little low, because why, I'll tell you. Now there is one thing which you have to do here. The coil resistance is put to 12. Now if the coil resistance is more, when it's running the clockwise direction, there will be the energy stored inside the coils, and that will make the stepper motor not exactly stop. When you're saying stop, it will run for some more time. So that is the behavior of any object in the world. Any object will have the tendency to continue in its state. Now if this tendency is not there, you would have not seen the accidents on the roads. It is not possible to stop something immediately. Now what I'll do is, now I'll just remove this coil resistance, make this coil resistance. You cannot make it to 0, because 0 is not possible. If I give 0, it will not take. I'll just see value must be positive. What minimum I can give is 1. Now this is fine. Now I'll show you. Now it'll just observe the equal movements of clockwise and anti-clockwise direction. Now I'll run it again. Now after doing the changes, I save it, say run the simulation. Simulation is running now. So the clockwise for some duration, stops, anti-clockwise now. See, it's running for the equal number of time. Now in the clockwise. So now in the anti-clockwise, and you can observe here also, red means it is 1, logic 1. Now observe here, red means 1. No, observe, keep observing here. This is P0.1. See, P0.1, P0.11 is high, it is running in the clockwise. Yeah, when both are low, current is when P0.8 is high, current 0.8 is high, it is running in the anti-clockwise direction. Now I hope you people understood. Now I wanted to show you one more thing here. Now is it possible to connect one more stepper motor here? Yes, it is possible. I've stopped the simulation now. I'll just copy this, copy the clipboard and paste on the clipboard here. Now I'll connect 11 to this, or let me do this here, and 14 here, and 2 I'll connect it to 9 also. Sorry, not 9. I have to do Control Z. 2 is connected to 15. Another 10. One more input, and 11 P0.7 is connected to 15. That is what I'm doing. Now I'll save this. Yeah, and for this also let me remove. Yeah, it's already, because I did a copy of this. Save and simulate. Now you can observe both the motors running. So both of them are running in the clockwise, because I've given the same input to this also, and both of them will start running in the anti-clockwise direction. Now using this driver, can I go for connecting 2 stepper motors? No, not possible. Using this driver you can connect only 1 stepper motor, because stepper motor will be having 4 terminals. I'll show you later when we go there. Okay. Now what if I want to, when this is running the clockwise, I want to make this run in the anti-clockwise direction? That also you can do. Only thing is simple changing. This 11 I've connected here right now. Sorry, right now. Now let me remove this, delete this wire also. 11 let me connect here, and 14 let me connect to this. Save. Similar. Now you have this running in the clockwise. When this is running in the clockwise, this is in anti-clockwise. Opposite they run. See, that is in the clockwise, this is in the anti-clockwise. When the upper one goes anti-clockwise, this will go clockwise. Yeah, this is the DC motor. I hope you people understood. You don't have to connect two DC motor. One is enough. One, if you connect and if you run, it's fine. Now I have one more example also to show you. Let me stop this simulation. Instead of this driver, what I've done is I have made my own design, which can substitute this. But I suggest you people to use this. Okay. I'll just open one more. Let me close this entire thing. Now I have here yeah, DC motor, yeah, without the driver. So this is already done, and all connections are made. I won't be changing the connection. If you want, I can zoom it a little bit. Yeah, this is what. Now there is no controller that L293D I'm not using. Instead of I'm using the relays and this is the DC motor and P0.8, P0.11. So this is not required for you, just to show you how that driver will control the motor and I have put two LEDs also here just to show you the flow of data here. I'll just run this, just observe. And I have two relays. Keep observing. When this LED goes on, this relay will on. So the power supply from the power supply that goes via this relay, this rotates in the clockwise direction. Now when this goes on, this relay will go off. This relay goes on, and this will run in the anti-clockwise direction. So this is not at all required for you. Just for showing, I shown how that driver will control